Hello and welcome to part 2 of Kinematics equations. My name is Mariah, and in this segment we'll be doing practice problems for kinematics equations. Example number 1. To find the height of a power line, you decide to throw a ball straight upwards. The ball passes the line on the way up after 0.75 seconds, and it passes it on the way down after a total of 1.5 seconds. So that's the time it takes to get from here to here. For part A, we are asked to find the initial speed of the ball. So we know that it takes the ball the same amount of time to get from the power line to the top of its path as it does for it to go down from the top of its path back to the power line. So the ball would reach the top of the power line at a time equidistant from 0.75 seconds and 1.5 seconds. And this time is the average of both of these. So to find that, we're going to do 1.5 plus 0.75 divided by 2, and that gives you the time of 1.125 seconds. Now, we know that at 1.125 seconds, the ball was at rest because it was at the top of its path. And we also know that it had an acceleration of negative 10 meters per second squared. So, knowing all this, we can use equation number 1 to find the initial velocity. So, we know that our final velocity is, I'm trying to find a place to write this, 0. It's equal to the initial velocity plus acceleration times time. And you do a little bit of solving, and you get that your initial velocity was around 11.3 meters per second. Now for part B, you want to find the height of the power line. I think I'll just draw a little line here so you guys don't get confused. So, to find the height of the power line, we're gonna use equation number 3 because we know that we crossed it at 0.75 seconds. Our initial velocity was 11.3 meters per second, and our acceleration is 10 meters per second squared. So you have the time, the initial velocity, and the acceleration. And if you're looking for the displacement, then equation 3 is what you want to use. So our change in displacement is equal to the initial velocity multiplied by the time plus 1/2 times the acceleration times the time squared. You do a little bit of solving, and then you get that the change in displacement is approximately 5.66 meters. And so you know that the height of the power line is 5.66 meters. Example number 2. Roger drops a ball from rest at a height h above the ground, and it hits the ground at a time t. Now, at what height should the ball be released so that it hits the ground at a time 3t? So, if we look over here at our answer choices, we can see that they are all given in terms of h, which is the original height that the ball was dropped at. This means that to find our new height, we need to find out how much bigger it is than our original height. In other words, we need to find the ratio of our new height to our original height. So let's start by finding the height the ball should be dropped from the ground to hit at time t. Okay, so we know the acceleration of the ball, negative 10 meters per second squared. We know the time, t, and we know the initial velocity. It's 0 because the ball is dropped. If you throw the ball, then it would have an initial velocity that's not equal to 0. Anyways, the equation that has all these things and can give us what we want is equation number 3. The height is equal to the initial velocity times the time plus 1/2 times the acceleration and the time squared. So I'm just going to plug in our values here. The height is equal to 0 times the time. This does nothing. Plus 1/2. And here for the acceleration, I'm going to use the variable g. Now, g is a variable that you use to represent the acceleration of an object in freefall near a planet's, in this case Earth's, surface. And that's going to be multiplied by t squared. Okay, and then we're going to simplify it, and we'll get that the height is equal to 1/2 g times the time squared. Now let's find the height of the ball so that it hits the ground at a time 3t. So again, we're going to plug stuff in. The height is equal to 0 times the time, that does nothing, plus 1/2 times g, which we know means negative 10 meters per second squared. And this time it's going to be multiplied by 3t, and remember to square the whole thing. Anyways, we will simplify, and then we'll get that the height is equal to 1/2 times g times 9t squared. So now what's left is to compare this original height with this height when the time to hit the ground is 3t. So we know that the height at 3t is equal to the original height times some number x. So now we're just going to replace the variables for height with the actual equations or expressions that we found. So 1/2 g times 9t squared, can't write that, is equal to 1/2 g times the time squared, and all that is multiplied by x. Now, we can cancel things on both sides, like this 1/2, like this g, and this t squared. So what's left is this 9 and this x. So we get that 9 is equal to x, and since x is what you're multiplying to h to get your new height, we know that our new height is equal to 9x. 9h, sorry. My bad. Example number 3. An alien holds a stone 20 meters above the surface of planet Ooga Booga. The stone is thrown upwards at a speed of 3 meters per second. The stone reaches the ground 2 seconds after it is thrown. The atmosphere of Ooga Booga has a negligible effect on the stone when it is in freefall. In other words, ignore air resistance. For part A, we want to determine the acceleration due to gravity of the stone when it is on Ooga Booga. Now, before we solve for the acceleration, I'd like to go over some misconceptions people might have about this problem. If you'd like to see the solution, you can skip ahead using the timestamps in the description box. Most people take issue with the fact that we don't know how far the stone traveled upwards, and so we don't know its total distance. And in that case, all we know is that the stone started with a velocity of 3 meters per second, and that it took it 2 seconds to complete its path, but we would need one more variable to be able to solve for the acceleration. But remember, the change in x variable asks us to input the displacement, not the distance traveled. The rock would have started in the alien's hand and then ended up on the ground. And as the diagram shows us, the shortest distance between these 2 points is 20 meters. But, you might say, if we use a displacement of negative 20 meters, then it would be as though the stone had been thrown down with a speed of 3 meters, and we wouldn't account for the fact that it had gone up some distance. And this is not true either, because if the stone had been thrown straight down, then its starting velocity would be negative, and the math would come out differently. Besides, remember that if you were to throw the rock down, the time of 2 seconds wouldn't apply, because that time accounts for the whole trip up and down. Now, we know the displacement, which is negative 20 meters. We know the initial velocity, which is positive 3 meters per second. And we know that the time is 2 seconds. And we're looking for the acceleration. The thing that can help us get the acceleration is equation number 3. The change in x is equal to the initial velocity times the time, plus 1/2 the acceleration times the time squared. So we're going to input our displacement, and remember it's negative because we're going down, negative 20 times our initial velocity of positive 3 times the time of 2, plus 1/2 the acceleration, and the time of 2 squared. So negative 20 is equal to, this is 6, plus 2 squared is 4, 4 divided by 2 is 2 times the acceleration. Move 6 to the other side, negative 26 equals to a, and that gets you that a is negative 13 meters per second squared. Example number 3, part B. How does the speed of the stone when it reaches the ground compare with the speed of the stone when it is thrown upwards? So when the stone is coming down and it reaches the same height that it was thrown from, its speed, which is the positive version of velocity, will be 3 meters per second. And remember, this is because the acceleration is constant, the distance from the top is the same, and the time to go that distance is the same. Since the rock is moving downwards, which is in the direction of acceleration, it will speed up, and thus its speed will be greater than when it was thrown. Example number 3, part C. How would the motion of the stone be different if it were thrown upwards at a speed of 3 meters per second from a height of 20 meters above Earth's surface? Explain in terms of the stone's maximum height above the ground, the speed at which it reaches the ground, the time for which it is in free fall, and its acceleration due to gravity. Okay, this is going to be a bit of a long one. So the acceleration of the stone due to the gravity on the planet Earth would be negative 10 meters per second squared. And this is a smaller magnitude than that of the acceleration due to gravity on Ooga Booga, which, if you remember, is negative 13 meters per second squared. So when the stone travels upwards, it is going opposite the direction of acceleration, which acts downwards. And this means that the stone will slow down. Since the acceleration is greater on Ooga Booga, it will slow down more quickly on Ooga Booga, and so it will not go as high. Now, when the stone travels downwards, it goes in the direction of acceleration, which acts downwards, and this means that the stone will speed up. Since the acceleration is greater on Ooga Booga, it will speed up more, and the final velocity will be greater than the final velocity of the stone on Earth. And as was said before, since the acceleration on Ooga Booga is higher, when the stone is going up, it will slow down more quickly, and so it'll take less time to get to 0 meters per second and reach its maximum height than if on Earth. Then, when going down, it will speed up more quickly, and so it'll take less time to reach the ground. You could also figure this out by taking the equation that the acceleration is equal to the change in velocity over time and flipping it by multiplying the time to both sides and then dividing by acceleration. And then you'd get that the time is equal to the change in velocity divided by the acceleration. And because it's in the denominator, the greater the acceleration is, the smaller the time is. Since the acceleration is greater on Ooga Booga, the time to reach the ground is less. Our next video will be on frames of reference. If you like this lesson, please consider liking, sharing, and subscribing. We'll see you next time!